So, right, where did we leave off last time? So we got to, let's go back. So we have this semigroup gamma A, semigroup generated by matrices like this, although in a minute won't really matter what they are. A in some alphabet, only a semigroup. We'll take the even words so that every element, every fraction is uniquely represented in this way, every fraction that arises. We had this representation number, Rn of n was a sum of matrices in some ball, let's say L infinity ball of size n. In other words, all the entries are of size at most n, and the 1, entry is the largest one anyway. So that's cutting off like that. And then the indicator function of whether this integer n is equal to the 1, entry. And the way to catch the 1, entry is to take the inner product with v equal to e1. E1 is 1, 0. I guess I've written it this, I don't know. Okay, transpose, whatever. Now it's a column vector instead of a row vector or something. Right. This, by elementary Fourier analysis, is recovered by taking the Fourier transform and taking the inverse Fourier transform, where the Fourier transform is nothing but replacing the indicator function by an exponential of all of size n, e to the 2 pi I theta, v gamma v. So far, so good. We decompose this integral 0, 1 into
baby Fourier,
right? Into the major arcs and the minor arcs. We introduce this notation WQK, which isn't the only way. There's a variety of ways to decompose the circle. This is the one that will work in our setting, but there's a lot of flexibility here. So this is the set of fractions theta equal to a over q plus beta, where q is between, let's say, q and 2q, a and q are co-prime. So this runs over all a co-prime to q, and beta is in a range k over n for where, okay, let's zero in on this minor arc. So this is going to be a main term, and what we need to show is that the error term in L2, the sum of these error terms in L2 over n, which by the way is the same thing after Parseval as the integral over the minor arcs of Rn hat squared. What we need is that this is little o of what it would be individually. So individually, the main term is of size, right? I didn't say that here. So R hat n of 0 is the number of elements in gamma A in a ball of size n, which is n to the 2 delta, roughly speaking. And so the main term will be n to the 2 delta over n. On average, we should get n to the 4 delta over n squared times n. So if we get little o of this, that is what will give us density 1. Instead of individual error terms being of size n squared over n, the average error term in L2 is of size n squared over n. And there's n of them.
Professor, I think this would be Rnn, not Rn hat theta, right?
So Rn of n is the function on the integers, and the dual of that is the function on the circle.
I agree, but you've written below this line, you've written Rn theta hat. Yeah.
I've written Rn hat of 0. When theta is equal to 0.
Okay. Then I agree.
So this is all ones, and that's just the number of elements in a ball. Sorry. Okay. Now this minor arcs we decomposed. So what is minor arcs? We decompose this as a sum over q going up to n to the 1/2. This parameter m, which we chose to be n to the 1/2. So this is a dyadic decomposition of the q's, and then a sum over k less than, again, m over q, also dyadic, where when we think of q as being n to the alpha and k as being n to the kappa, kappa goes up to 1/2, alpha also goes up to 1/2, and alpha plus kappa is at most 1/2. This is Dirichlet's approximation theorem. And there's a region here, alpha 0 and kappa 0, where we have major arcs. This is the major arcs. Everything else is supposed to be the minor arcs. And so in this minor arc sum, we have the restriction that either alpha is equal to, alpha has to be either bigger than alpha 0 or kappa has to be bigger than kappa 0 to be in the minor arcs. Otherwise, we're in the major arcs and we're going to do something completely different. And then we integrate over this region, WQK, of r hat squared, Rn theta squared d theta. Okay, that's as far as we got last time. Any questions? Let me pause for a second. So far, so good. We remember all these parameters. There's going to be a lot of parameters. So every time we revisit this subject, we have to load them all into our brain. All right. So let's go. This is what we need to estimate. Now, what is the size of WQK itself? In other words, it's a bunch of intervals, right? WQK is a bunch of intervals. What is the total length of those intervals, roughly? I mean, let's do it really roughly. So how many Qs are there?
About Q many?
There's QQs. How many A's, roughly?
About Q.
Yep. And how big is the interval for each fixed A and Q? What's the length in the beta variable?
And then K over N.
K over N.
Okay, and then Q is N to the alpha.
Yes, Q is N to the alpha, where alpha is at most a half, and K is N to the kappa, where alpha plus kappa is at most a half. This is from Dirichlet approximation theorem. So if that's what this interval is, and there's only, the sum is over log many terms. This dyadic decomposition has length log, right? We discussed this last time, I think. So if we're going to be going for a power savings here, losing a log or two does nothing. Or even it doesn't have to be a power savings. It can be like in the prime number theorem, e to the minus constant square root of log n or something. Something that saves more than an arbitrary power. So the fact that we're losing a couple logs here means nothing. So in order to estimate this sum, let's say in L infinity, to estimate just in L infinity meaning take the worst size of this times the length. We need an estimate. We need for theta in this region WQK, we need an estimate r hat theta to be little o of not just n to the 2 delta, which is the trivial bound, but we have to beat q squared times k. If we can beat q squared times k, then when we square this and integrate, we'll get this. Something's a little funny. Yes, when I square this, sorry. So when I square this, so I only need to beat k and q and k to the 1/2. So that when I square this, should I square it already? You can imagine when I square this, I have an n to the 4 delta, q squared k. That q squared k cancels out these guys. I get the 1 over, I pick up the 1 over n over the length. And now I have something smaller than n to the 4 delta over n. Nick, did I do that too fast? No, it's good. Leo, this makes sense?
Yes, but now it seems that the logs will cause a problem, though, right?
Well,
because you'll have for delta over n log n log n.
It depends on how good this little o is. This little o has to be better than these logs.
Okay. So we're aiming for something more precise than little o.
Exactly. We're gonna get more than just little o of this. We need a little more. Okay. So let's do it. How are we going to estimate this exponential sum? So here it is again, r hat n of theta. It's a sum over gamma in this weird semigroup that we know nothing about in a ball of size n, e to the 2 pi I theta, and then the 1, entry. Well, what we would like to do is apply, we talked about this a little bit last time. If we write theta as a over q plus beta, then we want to be able to apply harmonic analysis in this semigroup. Want to apply harmonic analysis in gamma. But we can only do that when beta, we can do that effectively when q and beta are small. We can do it in the major arcs. We can do this, and we haven't discussed this, but I hinted at it last time, can do this effectively, meaning with error terms that are smaller than the main term, when q and beta are small. So this is the major arcs analysis. But of course, we're not in the major arcs, we're in the minor arcs. The heck are we supposed to do? So this is where you're totally stuck. This is where the circle method begins and ends. You don't have a way to proceed. Okay, so new idea. Of course, all good ideas are just stolen ideas from somewhere else. So we're going to steal an idea from Vinogradov. Create bilinear forms. How? Forget about the original function, which was really capturing the true multiplicity. Replace Rn of n by this function, which I will continue calling Rn of n. And this is still a lie. This still isn't the real function. What we want to do is not sum over a single ball, but let's say a pair of balls, just to get started. So gamma 1 in a ball of size x, gamma 2 in a ball of size y, e to the 2 pi I theta, v, and then gamma 1 times gamma 2, v. So why has this helped? And x and y are new parameters that we're going to analyze. First of all, what should the size of x and y be? If I want this product to be of size n, so that we get an integer of size n, what do we want for x and y? What will be the size if gamma 1 is of size x and gamma 2 is of size y? What will be the size of the product as a group under the group operation? Go ahead.
Probably square root of n.
That would be where they're balanced. All I mean is where x times y is equal to n. So you're right that the balance term, maybe we want x and y both to be square root of n. Maybe not. You'll see in a minute that that's not what we always want. Or maybe we won't get to that today. Right, but the point is, look at the difference between. Now, what did Vinogradov do? Vinogradov did exactly the same thing. He created bilinear forms just by changing. You see, this is not the true. This is a theta and this is an n. So let's make this r hat theta. And then the corresponding. So now we're not capturing the true multiplicity. We're capturing some kind of twisted multiplicity. Right? We're taking a ball of size root n, say, and another ball of size root n, multiplying them together, and then seeing what numbers come out of that. But it still has the property, because gamma is a semigroup, when you multiply two elements, the definition of the semigroup is you multiply two elements, you're still in the semigroup. So any product of these elements is still in the semigroup. And so we still have the key property, still have that if this new R of n is non-zero, then n is represented and appears in the set of denominators. The only way a number arises here is if it arises in the original group. We might be missing some things. I don't know. We've bastardized the multiplicities, but it doesn't matter. As long as we are catching the non-zero aspect of the multiplicities, then we're still producing denominators of these uniformly badly approximable fractions. Linear
Can I ask you a question?
Oh, go ahead, Lewis.
So like in the original Vinogradov stuff,
Yes.
there's like an identity for sums over primes that gives you bilinear terms, right? So you're like capturing exactly what you want, but what you're doing here, I'm just trying to understand. So you're still using like bilinear stuff, but maybe sacrificing representing everything, but the point is just to represent many things or something like that?
Exactly.
Okay.
Exactly. So in Vinogradov, let's go back to Vinogradov. I mean, we haven't talked about Vinogradov. Vinogradov is just for people who have already heard of Vinogradov or seen what it is. Yeah. So one of the key ideas in Vinogradov. So for example, in Z, if you have a ball of size X and you add that to a ball of size Y, you cover a ball of size. This covers a ball in Z of size X plus Y. Right? You take an interval of size X. So one of the ideas, there's a variety of ways in which this creating bilinear forms idea can work. One of them is you have a sum over the integers, and then you realize, actually, I want to sum over pairs of integers that's free. And then when I sum those integers, well, I still get something that contains an interval. Doesn't contain it uniquely. There's some multiplicity, but I don't really care. I'm covering what I would be covering originally with two balls. But if you want to cover a ball of size n, you need x and y to be n over 2. If for x plus y to be n, the balanced, you could choose x and y to be n over 2. Here we get to choose root n. The group is a multiplicative group. So this hyperbolic growth of the group is very much going to be a big asset for us. This method is much more powerful here than just in the abelian setting. Okay. So let's say that this is our decomposition. Let's say that this is our bilinear forms for the counting function. Now what do we do? Well, we still don't want to do harmonic analysis in the group. That's what we're trying to avoid. How has this helped us? So there are two things you do. My entire career is two things: bilinear forms and what's the second thing that you do with Vinogradov once you create bilinear forms?
Circle packings.
Oh, circle packings. Okay. The applications are to many things. But there's only, like, I think every one of my papers, maybe not the most recent ones, but certainly in this stage of my career, every paper had two ideas. One is bilinear forms, and the other one is
Holder's inequality.
Which one?
Holder's inequality.
Holders, yes, Holder in the simplest case where it's called when it's L2, Cauchy-Schwarz.
Okay, that was my next guess.
Cauchy-Schwarz. Holders is the generalized Cauchy-Schwarz. Yes, Cauchy-Schwarz.
Right. That was just
there's a saying.
One of my friends.
Sorry, go ahead, Nick.
One of my well, I guess one of my friends had a advisor when we were undergrads, and one of his grad students said the only trick he's ever used is Holder. That's the only thing he's ever used in any paper. So it seemed like a good guess.
Yes, it is a good guess. There's a saying, to some people, Cauchy-Schwarz is an inequality. To me, it's a living. So So Cauchy-Schwarz. Okay, so we start with this R hat n, and immediately, reflexively, we have a pair of sums. In analytic number theory, we know we're supposed to either switch them. The only other thing you're supposed to do in analytic number theory, if you have a pair of sums, is Cauchy-Schwarz. So Cauchy-Schwarz, let's apply Cauchy-Schwarz. What will that give? So we only, you could say, well, so we have these two sums. That's R n hat theta squared. And let's sum over this. This will be the variable in which we Cauchy-Schwarz. So we have a sum over gamma 1 in gamma in a ball of 1 squared. And then we have a sum over gamma 1 in gamma in a ball of size x of this thing norm squared. Gamma 2 in gamma in a ball of size y, e of theta v gamma 1 gamma 2 v squared. So this is Cauchy-Schwarz in this variable. So I'm treating this as 1 times this thing. I have a 1 squared raised to the 1/2, but I'm squaring the other side, or this thing norm squared. So far, so good. Okay. In this first variable, there's nothing to do. There's nothing to save. So what do we have? How many elements are there in a ball of size x? In the semigroup, what's the growth rate of the semigroup?
Don't remember, so I'm trying to look back.
In a ball of size n, it was n to the 2 delta.
Oh, okay, right.
So in a ball of size
right,
x,
okay.
it's x to the 2 delta. Okay, which if x is root n, this is n to the delta. So we're what, quarter of the way to what we're allowed based on this, halfway to what we're allowed in this numerator. So half of it we just wasted. There's nothing we can do. Now here we're going to do some trickery. The first thing I want to do is use the fact that this is also bilinear. Not only have we constructed bilinear forms, the expression itself is bilinear in these gamma variables. So I can write this as the inner product of gamma 1 transpose v, gamma 2v. It's exactly the same thing. If I have gamma 1, gamma 2, I can move that to the other side. And now remember what this gamma 1 transpose v is. It's just a pair of numbers. It's like dB or whatever. It's the first column of gamma 1 transpose. But those are uniquely determined by the matrix. And what will the size of this? So this is some number. Let's call it. Let's call this y. Y is in Z2. And what will its size be? Gamma 1 is of size x. So its first column, or really its first row, because we're taking the transpose, is of size
X squared.
Each element is of size x.
Yeah.
Right? If this is of size, if we're talking about just like L infinity.
Okay,
norm.
I guess that's what I meant.
Yeah,
That's
it's
kinda-
just linear.
kinda what I
It's
meant.
linear, right? We haven't done anything to it. It's just linear. So this is also of size x. So what we're going to do is forget that we're summing in this weird set of y's. We have some very thin set of y's that occur. The pairs of y's that occur are exactly the RAs. That's what we're trying to understand. We're going to throw that out and sum over all y's in Z2 in a ball of size x. Now, instead of having a sharp cutoff, we should have a smooth cutoff. So let's introduce a smooth cutoff function, upsilon. This is my attempt at an upsilon. Leonidas, what's the right way to draw this thing?
Like this.
Like just like a U.
Yeah, just like a U. Yeah, maybe it's yeah. We go for eta usually when I write smooth, but it really doesn't matter.
This is how tech makes it look like a gamma with no. So it makes him look more like a V than a U.
It's a capital epsilon.
Yes, capital.
Okay, then it's drawn correctly.
Oh, good. Oh, very good. So it's the capital, yeah, capital upsilon. Okay. Y over X times this all sum over gamma 2 in gamma in a ball of size big Y, e to the 2 pi I theta times little y inner product gamma 2 V squared, where, so what do I want about this upsilon? This capital upsilon, I wanted to, so it's a function on R2. As a function, I'll draw it as a function in R1. I want it to be bigger than 1, whatever it's doing. I want it to be non-negative. And I want it to be bigger than 1 between -1 and 1. And I want its Fourier transform to be supported in -1, 1. Okay, so the support of the Fourier transform should be in -1, 1. Can you think of such a function? When you start making restrictions on a function and its Fourier transform, you have to get a little nervous, right? Heisenberg's uncertainty principle is living here. So does such an upsilon exist? I don't even want it to be, I don't need it to be smooth. There's
You
a
said you want
standard. Go ahead, Lewis.
Support in -1, 1 of the Fourier transform.
Yes,
Yeah, so like the tent function.
beautiful. The tent function. The tent function is exactly what I had in mind. The tent function, which is a convolution of the indicator of an interval with itself. Do you know what the, so if this is this tent function, just straight up to 1 or something and straight back down, do you know what the Fourier transform of that is?
Yeah, it's the square of the sinc function.
Exactly, sine x over x squared. So this thing, and you have to put in some constants to make it bigger than -1, 1. But whatever it does this. So it has some zeros, but it doesn't matter. It's non-negative, and put in some constants here to make sure that this happens. But it has sort of this bulk region here, and its Fourier transform is this thing. It says my internet connection is unstable. Did you miss any of that?
It was a little
you are
choppy at
cutting-
points.
Yeah, you're cutting
it's
in
okay.
and out a little bit.
Okay. Anything I can repeat?
No, I think I got all of that for this part.
Okay. Why is this a
It's-
square?
Oh yeah, I was gonna make a comment about this too. I was just gonna
Yep.
say it's like what we did about Fourier transforms, like convolutions versus products on the other side, right?
Exactly. Exactly. This is a convolution. This is an interval. This is an indicator function of an interval convolved with itself. If you take, what is it, a half? Excuse me. Maybe minus a half, something like this, convolved with itself. No, it won't let
Something like that.
something like that. It wouldn't have to be that small. There we go. Convolved with itself. So this tent function is the convolution of a function with itself, which means its inverse Fourier transform will be a product of a function with itself. And the Fourier transform of a flat interval is sinc sine x over x, which is why the convolution will be the product of sinc with itself, which makes it a square. Okay, so analytically, it's easy to come up with such a thing. And the point is, so this function is bigger than 1 on the support of this. And we have norm squared, so we have positivity. Okay, so that's why this is an upper bound. Does that make sense? But it doesn't matter which upsilon you take, just these are the only properties of it that I will use, but if you want an explicit one, one exists. Okay, let me bring here so we can stare at it. So we have x to the 2. Now we squared here. So remember, we needed to save, before we squared, we needed to save 2 times root. So we really need to save q squared times k and a little more. Let's keep track of what we need to save. So after squaring, we need, after squaring Cauchy-Schwarz, we need to save q squared times x plus a little more. Okay. Here we have a sum over y. And then when we open this square, we're going to have 2 sums over gamma, gamma 2 and gamma 2 prime. So we have a sum over gamma 2 and gamma 2 prime in gamma in a ball of size y, and then an inner sum on y in z2, upsilon of y over x, and then e to the 2 pi I theta, y inner product. So the nice thing about this inner product is that it's completely linear in the gamma variable. So in fact, we'll get gamma 2 minus gamma 2 prime v. You see that? We have 1 gamma 2. When we open the square, it's you multiply this with this number of absolute value 1 by another sum, gamma 2 prime, with the complex conjugate. And so when you multiply those together, you can collect terms. There's a minus sign on one of them, but this expression is an expression gamma 2 is completely linear. So it's just gamma 2 minus gamma 2 prime v. Okay. So far, so good. What are we going to do with the sum? All pairs of integers.
Reverse them?
We've already reversed. We just reversed. We have this y sum on the outside, the gamma 1 and gamma 2 sum. We reversed orders. After we reverse
unwind.
orders, what is it?
No, there's no winding. Okay,
There's
well,
no
we smoothed
wind.
it out. So what we had to smooth it for a reason.
We smoothed it out. It's because we're going to apply something that works best with smooth functions. If you have a sum over all integers, what's
Oh, Poisson summation. Of
Poisson
course.
summation? That's the next tool.
That took me too long.
Okay, bilinear forms, Cauchy-Schwarz, Poisson summation. That's it. Now you know my entire tool set. Okay, so Poisson summation. Poisson summation. Okay, so we have a sum over the dual k in z2. This is just in each variable. And then an integral over y in r2. What's the Fourier transform of this? Well, it's just this function time integrated. So this is upsilon y over x, e to the 2 pi I theta, y inner product, this gamma 2 minus gamma 2 prime v. And then e to the minus, what is it? K dot y dy. So k is a pair of integers, y is a pair of real numbers. This is catching the kth Fourier coefficient of this function, and you can sum over all the integer values of it, or you can sum over all of the integer values of its Fourier transform, and those two things will be exactly the same. This is equal to that. That's Poisson summation. Now in 2 variables instead of 1. So far, so good. Okay. Let's replace y by y times this parameter x. Then what will we get here? So when we start manipulating this integral, what happens to dy? When I rescale by a factor of x,
X times dy.
say it again.
X times dy.
X times dy would be correct if we were in one variable, but I'm rescaling each of the variables by x.
Right. Y is in R2, so we get x squared.
X squared, exactly. So a factor of x
course.
squared comes out. And then, okay, let's not do too much at once. Let me rewrite it again. Y in R2. Now I have upsilon of y. And now I have an exponential sum. E of, let's see, minus, let's do minus k dot, this has been multiplied by an x dot y dy. So that's just this term. And then there's another term, which is plus theta times x times this gamma 2 minus gamma 2 prime v, which is also being dotted by y. Here I'm writing the dot as an inner product. Here I'm writing it with a dot, but they're doing the same thing. So this is a vector in R2. I'm just combining these two things with y getting rescaled by x, but that rescaling I'm moving over to the other side. Does that make sense? So far, so good? Okay, but what is this? It's just upsilon hat. At something. Where?
kx minus theta x gamma 2 minus gamma 2 prime v over 2 pi.
Yes.
Yeah. No, not even over 2 pi. You've written in the character form. Yeah.
Exactly. Gamma 2 minus gamma 2 prime v. Beautiful. And I pulled the x to the outside. Okay. So let's summarize. Let's summarize what we have on our r hat n theta squared. So in total, r hat n theta squared, we've bounded by, first there's an x to the 2 delta. Nothing we can do about that. Then there's a sum over gamma 2 and gamma 2 prime in gamma in a ball of size y. The sum on y has been turned into a sum on k. Then there's a factor of x squared. There's a factor of x squared, which is going to come all the way out. And let me write it. Yeah, okay, fine. Let me just write it as x squared. There's a factor of x squared that's coming all the way to here. This is not an upsilon. This is a x squared getting wedged in there. And then I have the Fourier transform of upsilon at x times k minus theta gamma 2 minus gamma 2 prime v. Okay, that's as far as we got. Now, before we analyze this, let me make a little remark. Let me make a little remark. So far, so good. Let me give you a second to write this down. Give me a thumbs up when you're ready. Okay. They need us all good? Okay. Let me make a little remark. When we did this, when we replaced the sum over this semigroup where the harmonic analysis is difficult and not robust, we replaced that by all of Z2, where the harmonic analysis is completely classical and standard, and we have great ability to count in Z2. In this, so what we gain is harmonic analysis. No such thing as a free lunch. What do we lose? Harmonic analysis in Z2, in other words, Poisson summation, as opposed to in the semigroup. What do we lose?
Like boundedness or finiteness of our sum?
Well, we control the boundedness with this smooth factor.
True. We lost our semigroup structure.
We did lose the semigroup structure. That's true. We threw it away, but actually we wanted to throw it away because it was the semigroup structure that was making the harmonic analysis hard. We replaced it by all of Z2, where the harmonic analysis is nice. But how many points were there in this sum?
Like x to the 2 delta,
Yes. And how many points are there in this sum?
x squared.
X squared. So we have an x squared instead of an x to the 2 delta. So we lose an x squared versus an x to the 2 delta.
Is this why is this where we pick up the condition that delta has to be really big so that x squared looks kind of like x to the 2 delta?
Exactly. Exactly. This is one of the places where this loss is only justifiable or not, it doesn't kill you as long as delta is near 1. Okay, so this loss is only acceptable outweighs the loss not outweigh the benefit. Benefit outweighs the loss. The benefit outweighs the loss. This loss is only acceptable if delta is near 1. How near will depend on exactly will depend on some will depend on how well we treat this error term, this minor arcs analysis. Okay, so far so good. All right, great. So we've gotten this far. We've lost a little bit, and we're hoping that the amount that we lose by is enough to be able to the support of this upsilon is -1,1, right? And so in order for this to be non-zero, this doesn't equal 0 only when this thing is of size less than 1. X times k minus theta v gamma 2 minus gamma 2 prime v is less than 1. Now I'm being a little sloppy about, is this a circle or is this a square? Is an L infinity versus, there's some constants here that won't make any, won't play any role. In other words, i.e., only when whatever this number theta times gamma 2 minus gamma 2 prime v, wherever this is, minus some integer lattice, k, this has to be less than 1 over x. Now 1 over x is huge. X is root n or something. So how many integer lattices can participate here? How many values of k can occur? 1. This is some number. This theta, wherever we are, this is Z2. Z2, this theta times, I don't know where this vector is, wherever it is, theta times gamma 2 minus gamma 2 prime V is some vector. And it has to be within 1 over x of some lattice point. Well, it's only going to be within 1 over x, which is a tiny ball of a single lattice point. And in fact, for most lattice points, there won't be a single lattice point. For typical values of this thing, there's no reason for it to be that close. Okay, so at most, one value of k in Z2 is close enough. And for it to be close enough, so we need that the distance to the nearest integer of this vector, gamma 2 minus gamma 2 prime V, is less than 1 over x. That's exactly what this is. If there exists some k, then the distance to the nearest integer is at most, that's what this is. This is distance to nearest Z2. Okay. So this whole sum, and in that case, the value of this thing is whatever it is. It's bounded by 1. This is a single function, this upsilon prime. Epsilon prime is bounded uniformly. Right? It's telling me I have some unstable internet. So if there's something I need to repeat, please tell me.
I think I've got it all. It is a little choppy, but enough's getting through.
Okay. All right. Hopefully we'll make it work. Okay, so as of now, we have this r hat n of theta. By the way, we've never yet used that we're in the minor arcs. This is an L infinity bound for any value of theta so far. There's an x to the delta and an x squared. Let me write that as x to the 4 delta times x to the twice 1 minus delta. Just to make it apparent, we're expecting an x to the 4 delta times a y to the 4 delta. And this is how much we're losing. And of course, only if 1 minus delta is very small are we capable of losing this much. Okay. Then we have this sum over gamma 1 and gamma 2, sum over gamma 2 and gamma 2 prime in a ball of size y. And now the k sum has turned into an indicator function. So let's put less than because the value of this is 1 or something. And now we have the indicator function of whether the distance to the nearest integer of theta gamma 2 prime v is at most 1 over x. So if it's not, there's nothing to say at all. Okay. So far, so good. Now let's use the shape of this in the following way. If I look at A over Q times this gamma 2 minus gamma 2 prime V, that is the same thing as theta times gamma 2 minus gamma 2 prime V minus beta Now, the distance to the nearest integer of this is at most the distance to the nearest integer of this plus the distance to the nearest integer of this, which I will bound simply by its absolute value. This condition says that this is bounded by 1 over x. What do I know here? The gamma 2 minus gamma 2 prime, that's of size at most y. And what about beta? What's the size of beta? V is of size 1. In this region, so in for theta in WQK, beta is of size
It's K over N.
K over N. Okay. And Q is of size Q. So now is a good time to choose X and Y. So now we're going to choose X and Y to be root N. We have to choose them. We can't choose them depending on K. K is going to be changing. This decomposition, we're going to choose once and for all. So here we get 1 over root N plus a K over root N. So this is at most, let's forget about this 1, K over root N. But what's a lower bound on this? If gamma 2 is not congruent to gamma 2 prime mod Q, then the distance to the nearest integer, then the distance to the nearest integer of this thing is at least 1 over Q. And 1 over Q is of size Q. There's some constants here that you have to add into things to make this exactly, 1 over Q is of size 1 over Q. But K times Q is at most root N. But K times Q is at most root N. Alternatively, this K over root N is at most 1 over Q. So that means this can't happen. In other words, gamma 2 has to be congruent to gamma. The only reason why this number is so close to an integer is because gamma 2 is congruent to gamma 2 prime mod Q.
But we didn't care about the constants. Could it not be the case that it's like
Keep being careful with the constants.
But yeah, but all I'm saying is that it could be C over Q smaller than that thing, smaller
Yes.
than C capital over Q, and maybe
Yes.
it could happen, no?
So what you have to do is, before you do any of this, you break up the gamma pieces into balls of a small enough constant. This is taken care of in the paper. It's if you have, so you have gamma 2s, right? And the gamma 2s, you know, are of size y or something. So what you really do is you break things up into a bounded number of things where the difference between any two of them is, y over 100. So there's a way to throw in the constants. Okay, I can, if you like, I can show you where in the paper that's done, but that's sort of a minor point. There is a way to make this constant really be strictly less than 1 over Q. You're right that one has to be slightly careful there, and in the paper you'll see how we take care of that. And it's just what I said here. I mean, I've basically given it without doing the details. So what we've shown, so this theta times gamma 2 minus gamma 2 v being less than 1 over x can only happen if gamma 2 is congruent to gamma 2 prime mod q. If this thing's less than 1 over x, that only happens, it's too small for these two numbers not to be the same mod q. If they're not the same mod q, then this is at least 1 over q. But this upper bound gives us that it's at most 1 over q. And so the only way this happens is this. That means that when we go back here, we can replace this condition by the condition that gamma 2 and gamma 2 prime are congruent mod q. So now we have r hat of n squared is bounded by x to the 4 delta. There's a factor of some power of x to the 1 minus delta. Then I'm going to write these sums separately. There's a sum over gamma 2. And it's really this as a vector. I don't know about the other components. I only know about really gamma. This should really say gamma 2v is not equal to gamma 2v prime. This is only capturing the top row. Of course, we know that the top row determines the rest. The top row is unique, but let's just keep it like this for a second. So I sum over all gamma 2s in gamma in a ball of size y. And then I sum over all gamma 2 primes also in gamma in a ball of size y with the indicator function that gamma 2 v prime is congruent to this fixed number gamma 2 v mod q. So far, so good. I've replaced this indicator function of theta times this difference being at most 1 over x with this congruence. Nick, does that make sense? Great. Okay, but how do we capture this congruence? Oh, and one more thing. Once they're congruent, once I know that they're congruent, one more thing. Sorry, this should have gone. Once I know that they're congruent, then the distance to the nearest integer, once I know that gamma 2v is congruent to gamma 2 prime v mod q, that tells me that the distance to the nearest integer of gamma 2 minus gamma 2 prime v is just beta times gamma 2 minus gamma 2 prime v. And this thing is small enough that this is just equal to beta itself times gamma 2 minus gamma 2 prime v. And so for this thing to be less than 1 over x, that means that beta times this thing. So there's two conditions on gamma 2 prime. The second condition is that gamma 2 prime v minus gamma 2v is at most 1 over x times beta. 1 over x times beta. Sorry, that's hard to read. Let me rewrite it again here. Rn hat theta squared is bounded by x to the 4 delta, x to the 2, 1 minus delta. We're going to fix the value of gamma 2 for a fixed gamma 2. And then I have this condition on gamma 2 prime. Really, it's a condition on gamma 2 prime v. And now I'm going to do one more replacement of gamma 2 prime v by, let's call it z. Z in z2. So I'm going to write gamma 2 prime v as z in z2. I have the indicator function of z being in a ball. I have that z is congruent to something, gamma 2v mod q. And I have that z, the distance from z to this vector gamma 2v, is at most 1 over x times beta. Beta is of size k over n. Tell me if you follow all of that. So I have another loss here. So I'm again losing, instead of from y to the 2 delta, now there's going to be y squared terms. It's again the harmonic analysis, not even harmonic now it's down to counting. But counting in this semigroup, I can't do as good a job counting in this semigroup as I can in Z2. In Z2, I know how to count. This is easy. Okay, so let's estimate this. So we're in Z2. We have some fixed get vector, wherever it is, gamma to V. I don't know where that is. I want to know how many elements of Z2, forget that they're in a ball of size Y, even, let's drop that condition. How many elements are within a ball of radius n over xk and congruent to, so I can't take all of them. I can only take the ones that are congruent mod q. Congruent to this thing mod q. So I have to skip by q's to get to the next lattice point. So how many are there here? So first of all, how many elements are there in a ball of radius n over xk in Z2?
That many squared.
Yep, n squared over
And
x
then we
squared.
divide by q squared. Or, yeah.
Exactly. Divided by q squared. Exactly right, because I only get to take one out of q of them. No one's going to complain. Somebody should complain. Lewis, you should complain.
Like a plus O of 1.
Plus one. Plus one. Always, always, always when you're counting in integers and you say, well, there's this many guys and I only get to take one out of this many of them. There could be, if this number is less than 1, then you could be drastically underestimating the number of points here because there might be 1 point. Okay, so never forget this plus 1. So many great theorems die because of the plus 1. But in our case, let's think about this. X we've chosen to be root n. So x, if you recall, where do we set x to be root n? Yes. We've chosen x to be root n. So this is n squared over root n squared. So that's n over k squared q squared. But remember, the Dirichlet approximation theorem says k times q is going to be less than root n. So this fraction is already
It's 2.
well, it's already bigger than, so if I divide by qk and I square, this thing's already at least 1. So in fact, this plus 1 is extraneous
Okay.
in this case, but never forget the plus 1. But now we're done. We have that r hat theta squared is bounded by, here's an x to the 4 delta. We've lost x to the 2 times 1 minus delta. How many elements? So this is an estimate for the number of elements of gamma 2 prime, which we replaced by z. It's just n over x squared, k squared, q squared. How many elements here are there?
Y to delta, right?
Perfect. Y to the 2 delta. And then there's this factor of, I'm sorry, yes, that's right. That's right. Is that right? Let's see. Yeah, that's okay. So there's an n. So there's a y to the 2 delta, and then there's an n, which I'll write as x times y over k squared q squared. All right, we got to put all this back together. We have to put all of this back together. This is a y to the 3 delta. This is an x to the 5 delta. Good. Good. Okay, very good. So let's put all this back together. What is the total power? Remember, x and y are both root n. X and y are both root n. So, so what do we have? Here's an n to the 4 delta. I'm going to deal with this in a minute. I have an n to the 4 delta, n to the 2 delta, another n to the delta. Hang on a second. This is 4, 6, 7, 8. No, that's right. That's right. That's right. That's right. This is n to the 4 delta times something, times n to the sum multiple of 1 minus delta. So let's figure out what that multiple is. N to the 4 delta would be an x to the 4 delta, y to the 4 delta. Here I have a y to the 2 delta. X is equal to y. So I could write this as y squared. Okay, so this is
Wait, the x to the 4 delta should become an n to the 2 delta, right?
yes.
Okay, and then where do we pick up the other 2 n to the 2
So
delta?
here's an n to the delta,
Yep.
and here's an n, which I will write as n to the delta times n to the 1 minus delta.
I see. Okay.
So that'll pick up n to the 4 delta. There's one delta here, another delta here, and 2 more deltas here, n to the deltas.
Okay, and then I see 3 1 minus deltas.
There's 1 minus delta here,
sorry.
because there's only half,
2 1 minus deltas.
and then a 1 minus delta here. So there's 2 1 minus deltas. This is our loss. What's our gain? Q squared. Remember, we had to beat Q squared times K. And we did it by a factor of K. So as long as K is bigger than n to the 2 times 1 minus delta, this wins. Okay. So going back to our picture of alpha and kappa, kappa, alpha, a half. So this K0 had better be so small that it's smaller than than whatever this is, this exponent, small enough, K0 small enough. Sorry, K0 large, as long as K0 is large enough, that kappa starts at least at this exponent. As long as if kappa 0 is greater than 2 times 1 minus delta. Then we have our savings in this range. So we're not done. We're not done. This is the major arcs. We have something else that we have to do in this range. Let me pause here. Does this make sense?
I don't think what you've drawn has shown up yet. We can see the little, oh, here it comes. Here it comes. It's starting to appear.
Oh, God.
Okay, there we go. Now we have, oh, there's more. Okay. I think
So
we
there's a
have
delay from when I draw it to when it arrives.
Yeah, in that
but not the
particular
audio.
moment, it was significantly worse than it had been for most of the lecture.
I see.
Oh yeah, wow, things are still appearing. But
I'm not writing anything. So anything that you're seeing is
uh,
was written a while ago.
yeah, there's been a little delay. I'll lecture, though it's usually been pretty small.
Okay.
I guess the all the delay cancellation failed here. This is the major arc of the delay.
Right. Right. Okay, so does this make sense? So we've managed to
okay.
successfully estimate the minor arcs in this range by a power. By a power. So we don't care about the logs that we're losing. We have to worry about the range of very small beta, in which case we have to save a lot more from the alpha sum, from the Q variable. Okay. So we're not going to be able to do this today, but let me set something up for, let me start setting something up for next time, which is the following. So what remains is to estimate the integral over WQK of R theta squared d theta when K is small. K is n to the kappa, and kappa is less than kappa 0, but Q is large, Q being n to the alpha, and alpha is bigger than alpha 0. So in order to do this, now we're going to do Kloosterman type. So far there was no, this was just L infinity bound. This is like the standard circle method. We just did an L infinity bound. We didn't get any extra cancellation in anything. Okay. Let me introduce the following notation. Let P sub Q beta be the set of theta equal to A over Q plus beta. But now beta is fixed. So for fixed beta, Q is of size Q, and A and Q are coprime. And here's the Kloosterman refinement, Kloosterman type refinement, or Kloosterman analysis. Some people call this a refinement. Some people really don't like that it's called a refinement. It's a completely different method. Kloosterman type analysis is we want cancellation, want to try to get cancellation, Since we need cancellation in Q, Q has to play a crucial role. Let's isolate the role of Q, keep beta fixed, try to get cancellation in the sum over theta in P Q beta of Rn at beta, just to the first power. This is a beta. Okay. So the reason we would think to look at such a thing is it's from the Q behavior that we need to get the cancellation. So if we can take this sum, and what we're going to do, what's it called? Not preloading, not pre-image. Oh, come on. When you're saying what's about to happen in the future.
Predict.
Well, predict like a premonition, but not a, God, the word's on the tip of my tongue and yet I can't get it out.
Foreshadowing?
Foreshadow. Yes, thank you. Foreshadow. Okay. So foreshadowing to next time is that we'll look at this Rn. The Rn, now we have to put absolute values on this thing. So a sum over theta in this set PBQ will put some number of absolute value 1. This thing has absolute value 1 times Rn theta. Rn theta is a sum over gamma 1 in a ball of size x, and then gamma 2 in a ball of size y, e to the 2 pi I theta, v gamma 1, gamma 2, v. Sorry, I ran out of room there. Hopefully you can make sense of that. Actually, since we have the technology, we can use the technology. Ah, amazing. Okay. Okay. And then we're going to pull this out again, and we'll Cauchy-Schwarz in all 3 variables. So we'll pull gamma 1 out, and sorry, we'll Cauchy-Schwarz in gamma 1, Cauchy-Schwarz in gamma 1, which means we want cancellation, not just in the gamma 2 sum, but in the Q. There's going to be a Q and a Q prime, and an A and an A prime. What's the size of PBQ? PQ beta. What's the size of PQ beta? Roughly. How many Qs are there?
Q.
Q. And then there's how many A's?
Also Q.
Also Q. Okay. So now we're going to have 4 things to sum over in Q and Q prime and A prime. And then there's going to be a gamma 2 and a gamma 2 prime. So we're going to want cancellation in all of these sums with this gamma 1 getting pulled out. And we're going to, we'll see this extra cancellation will give us more Qs. If we can handle it, it'll give us more Qs. And part of the Kloosterman refinement is, do you want to just cancellation in A? This is like a second Kloosterman refinement. A first Kloosterman refinement is just getting extra cancellation in A. A second one is getting it in A and in Q. A third would be to play more games with beta. And this is in fact how improvements on what Bergan and I did go, by doing extra Kloosterman refinements. So we're jumping straight to a second Kloosterman refinement because that's what I know actually works. The first, should we take the time to work out why the first Kloosterman refinement doesn't give us what we want? Or should I leave that as an exercise? So here, this is a really good exercise. If you want to be prepared for class on, what's today, Friday? So class on Tuesday, here's an exercise. Try to follow this, try to work this out yourself with only first Kloosterman refinement, which would be a sum over theta in PQ of Rn hat theta, where P little q B is the set of all A over Q plus B, where A and Q are co-prime. So if we want to get extra cancellation just in the with Q and beta fixed, it turns out that you don't get enough savings out of that. At least not as far as we could see. There was no way to get extra. In fact, okay, I'm out of time, but I'll show you why next time. Maybe I'll make. We've been on this topic for so long, I kind of want to move on. So really do this exercise if you want to get a flavor for this theory. Otherwise, we're going to jump straight to the second Kloosterman refinement next time. Any questions?
I'm a little bit confused. We have Rn hat, and now we are summing over angles. How can summing over angles would help? It seems as if we should integrate over theta and sum over n. At least that's the usual Fourier thinking. Now you sum over angles.
So,
what's the idea? I'm a little bit confused.
Yes. So when we integrate over W, Q, K of R hat theta squared, right? This is the main thing. This is going to be an integral over beta of size K over N. And then we can pull out one factor. So then a sum of P, Q, beta for any fixed beta, it's a sum over theta in this PQ beta, R n hat theta. We're going to get cancellation on this, and then we can use the L infinity bound. What will happen is that we'll use the L infinity bound on this. That pulls all the way out, and then we have this extra summation, and then we integrate on beta. So we're trying now. We have given up on getting cancellation from well, so there's this sum in theta, and then the integral is d beta. So we've given up on getting more cancellation from the beta integral than we did already in this L infinity bound that we already attained. And then we're going to try to get extra cancellation in the A and the Q. And then outside of that, we just integrate trivially over beta. So this will only work in the range where beta, where this kappa is very small, where K is small, which is the only range that we care about at this point. That's a little bit of foreshadowing, not pre. That's why I stuck on the word. It's for, not pre. It's a little bit of foreshadowing of what's to come.